This aircraft is called the pinnacle of engineering and, at the same time, a $120 million flying disaster. The Bell V-22 Osprey is the only production tiltrotor in the world, which was supposed to rescue hostages, but instead claimed dozens of lives and nearly destroyed the Pentagon's reputation. Who in the Pentagon's leadership falsified test reports while coffins with pilots were returning to bases? What hidden danger in the tiltrotor's aerodynamics did NASA experts try to hide from the press? And why did billions of dollars continue to be poured into a project that, at the time, was virtually churning out uncontrollable machines? Watch this video to the end. We will analyze the fatal mistakes of the designers, the heavy lobbying behind the scenes of the Senate, and find out why the military still cannot abandon this dangerous hybrid. Let's begin. Somewhere at an airfield in the United States of America stands a machine that is hard to compare to anything else. It has a wing like a regular airplane. But at the ends of this wing are two huge rotors pointing upwards, like those of a giant helicopter. The engines are already warmed up, and the air around vibrates with a roar. In a minute, these rotors will begin to turn. The machine will smoothly, without a run-up, lift off the ground strictly vertically. And then, having gained speed, it will tilt the nacelles with the rotors forward and fly like a regular airplane, at a speed that helicopters have never dreamed of. This can be compared to a car that, in the middle of a highway on the move, turns into a train without slowing down. It sounds like something out of science fiction, but that is exactly how this machine works every time it takes to the air. This is the Bell V-22 Osprey. If you have never encountered tiltrotors before, here is the essence in 2 words. It is an aircraft that combines the capabilities of a helicopter and an airplane in one machine. It takes off and lands vertically like a helicopter. It flies at high speed and over long distances like an airplane. The first flight of this machine took place in 1989. The development was carried out by 2 large companies at once, Bell Helicopter and Boeing Rotorcraft Systems. Creating such a machine took about 30 years of continuous work, a period during which a person has time to graduate from college, raise their own children, and see them go to work themselves. And all of this cost tens of billions of dollars. And here is what is surprising. Decades after its first flight, the V-22 Osprey remains the only production tiltrotor in the world. Not a prototype, and not an experimental machine for air shows. It is a machine that works, and today it is still used as part of the Marine Corps and Special Operations Forces of the United States of America. One such machine costs roughly from $110 to $120 million. Other sources name a smaller figure, about $66 million. But even at the lower limit, this is an amount for which you could build a small passenger plane and still have funds left for several years of its maintenance. In total, American industry has produced more than 200 of these machines. This is not a single experimental project. It is a whole program that is stretched over decades and spans several generations of engineers. But there is one oddity in this story that may seem illogical. The V-22 Osprey is simultaneously called a true miracle of engineering and the most popular target for jokes and ridicule in its own country. How can the same machine be both the pride of engineers and a reason for jokes? The answer lies in a story that began long before the first flight of the Osprey, and it began not in a design bureau. It began with a failure for which a very high price was paid. April 1980. In the desert near Tehran, a complex rescue operation is being prepared. Several months earlier, a revolution occurred in Iran, and a group of American citizens were held hostage on the territory of the Embassy of the United States of America. Negotiations had reached a dead end, and Washington decided to act by force. The plan looked logical on paper. The special forces land at an abandoned airbase in the desert. From there, the group covertly makes its way to the capital, frees the hostages, and returns by the same air route by which they arrived. Everything was supposed to take one night. On April 24, 1980, the plan began to be put into action. C-130 Hercules transport aircraft delivered special forces to an intermediate point in the desert. Helicopters were also supposed to fly there for the further transfer of the group to the city. And this is where the problems began. Out of the 8 helicopters that flew out on the mission, not all made it to the assembly point. Some machines encountered technical problems right in flight. Some got into a sandstorm and were forced to turn back. A simple detail. The task required a minimum of 6 operational helicopters. By the time of the assembly, fewer were left in service. Formally, the operation was already under threat of failure even before the group had time to approach the city. The command made a difficult decision to cancel the operation right at the assembly point in the desert. But this is where the next, most tragic episode occurred. During preparation for departure, one of the helicopters collided with a C-130 tanker. As a result, several American service members were killed and equipment was lost. The hostages were never freed. The operation, codenamed Eagle Claw, ended in a complete failure, which was reported by world news agencies the next day. For the American military and political leadership, this was a severe blow to their reputation. After the incident, a special commission was established to analyze the causes of the failure, and the conclusion it reached was unexpectedly simple but extremely unpleasant for the military. It was not about the training of the special forces, it was at a high level. It was not about the plan itself. In theory, it was quite feasible. The problem was the technology. At that time, the American Army simply did not have an aircraft capable of solving 3 tasks at once: flying a significant distance, taking enough people and cargo on board, and doing so without a long runway. Transport planes could not land just anywhere. Helicopters did not have the necessary flight range and carrying capacity for such a mission. An absurd situation arose. 2 technologies, the airplane and the helicopter, had existed for decades, but neither of them individually was suitable for the task that reality set before the military. Something fundamentally new was needed, something in between. The commission recorded this conclusion in an official report. And this report launched a chain of events that, 9 years later, would lead to the first flight of the machine we are talking about today. The Military Department of the United States of America did not drag its feet with the conclusions. Already in 1981, just a year after the failure of the operation in the desert, a new program started. Its working name sounded dry and military, JVX, which stood for Joint Service Vertical Takeoff/Landing Experimental Aircraft. Behind this formal name stood a truly daring idea: to create a machine that would solve the problem that came to light in the desert near Tehran in one fell swoop. A machine that takes off without a runway, flies fast and far, and at the same time takes enough people and cargo on board. The program was to be supervised by a separate commission, and this was not just a formal body for show. It included representatives from several structures at once: the Army, the Air Force, the Navy, and the Marine Corps. Each of these structures pursued its own interests and made its own demands on the future machine. Not only American companies were invited to participate in the competition. True heavyweights of the industry fought for the contract: Bell, Boeing, Lockheed. Foreign developers also offered their options: the French company Aerospatiale and the British Westland. It would seem that with such a number of serious players, the struggle should have unfolded between them directly, each for themselves. But it happened otherwise. The Bell Company, which had many years of experience in creating helicopter technology, made a decision to unite with its direct competitor, the Boeing Company. At first glance, a strange step. Why unite with a rival instead of fighting against them? But there was a clear logic to this decision. Similar to how in team sports, 2 players with different strengths proved to be more effective together than alone. Bell at that time was considered one of the world's best specialists in rotors and rotorcraft technology. It was this company that took on the development of the wings, nacelles, and rotors of the future machine, and was also engaged in refining the engines. Boeing, in turn, possessed colossal experience in creating large and complex fuselages, flight decks, and electronic systems. It was Boeing specialists who took on the development of the machine's body, the cockpit, all the onboard electronics, and flight control systems. The result was an alliance in which the strengths of one company compensated for the weak points of the other. This division of labor proved to be so successful that it was preserved throughout the history of the program, right up to the present day. But it is one thing to distribute tasks on paper. It is quite another to embody an absolutely new concept of a machine in real metal. Ahead, years of painstaking work, first tests, and first serious disappointments awaited the engineers. May 1988. After several years of design, calculations, and endless approvals, the first prototype of the future machine finally stood on the flight field. Metal, composite panels, 2 huge rotors at the ends of the wing, all this ceased to be a drawing and became a real object. But almost 10 more months of checks passed from the finished prototype to the first flight. Engineers tested each system individually before allowing the machine to lift off the ground. And so came March 1989. The prototype took to the air. The moment toward which the team of engineers had been walking for almost 8 years since the start of the program had finally taken place. For the designers of Bell and Boeing, it was a true triumph, proof that their idea works not only on paper and not only in a wind tunnel. It would seem that from then on, everything should have gone smoothly. Tests, refinements, production. But reality turned out to be far harsher. In 1991 and 1992, 2 accidents occurred with prototypes of the machine. The program, which had only begun to gain confidence after the first successful flight, was again under close scrutiny and criticism. What is it like to spend almost a decade on development, achieve the first flight, and then watch 2 prototypes, one after another, encounter serious problems? This is exactly what the development team faced in the early 90s. Problems poured in one after another. The Army, which was originally among the customers and participants of the program, made a decision to withdraw from the project. This was a serious blow. The fewer branches of the military are interested in a machine, the fewer funds are allocated for its development, and the fewer machines will ultimately be ordered. And the number of ordered aircraft was indeed reduced. What was conceived as a large-scale rearmament program for several branches of the military began to shrink to more modest volumes. True debates unfolded in the Congress of the United States of America about the fate of the program. Some lawmakers insisted on a complete halt to funding, calling the project too expensive and risky. Others pointed out that there simply was no alternative to this machine, and the original reason for its creation, the tragic experience near Tehran, had not gone anywhere. The program was not closed, but the accidents did not end there. Ahead was an even more serious test of strength, a test that nearly put an end to the very idea of a tiltrotor as such. The year 2000. 2 accidents in a row, as a result of which 19 Marines on board were harmed. After this, the American command made a decision that seemed unthinkable after so many years and billions of dollars of investment, to completely stop the flights of all built machines. The ban was in effect for a year and a half. For a year and a half, expensive equipment stood idle on the ground, while engineers and specialists tried to understand exactly what went wrong. The answer was not found immediately, but it turned out to be connected with a phenomenon that was well known to helicopter pilots long before the appearance of tiltrotors. This phenomenon is called the vortex ring state. To understand what this is, imagine a kitchen fan that was set to work in a closed, small room. At first, it drives a fresh flow of air in front of itself. But if the air has nowhere to go, it begins to return back to the blades themselves, forming a closed ring flow. The fan continues to spin, but there is less and less use from this. It just drives the same air in a circle. Roughly the same thing happens to the main rotor of a helicopter under certain descent conditions. If the machine goes down vertically, or almost vertically, but at the same time fast enough, the rotor blades fall into the airflow that they themselves had previously created and thrown down. The rotor begins to breathe its own exhaust, so to speak. At this moment, the lift drops sharply and suddenly. Moreover, it drops not gradually, but in a jump, literally in seconds. This is what makes the vortex ring state so dangerous. The pilot may not have time to react to the change in the machine's behavior. For a regular helicopter, this problem is serious in itself. But for a tiltrotor, it turns into something much more insidious. The fact is that it has not one source of lift, but 2, one rotor on each end of the wing, working independently of each other. And here a truly dangerous scenario arises. What if the vortex ring state manifests itself not simultaneously on both rotors, but only on one of them? Then one end of the wing will begin to sharply lose lift, while the other continues to work as usual. The machine in this case can begin to roll uncontrollably to one side. For a machine that is physically unable to land like an airplane, smoothly descending onto a runway, this threat is particularly acute. It was with this phenomenon, presumably, that the accidents of the year 2000 were connected. The question was not whether to continue the program or not. The question was whether this problem could be solved technically at all, or if the design of the tiltrotor contained an unfixable flaw. After a year and a half of a complete ban on flights, the developers faced a choice that is rarely made in the aviation industry. Close the program permanently, writing off the spent billions as a lesson for the future, or understand the problem to the end and bring the machine to a state in which it can be trusted. The specialists responsible for the economic side of the issue approached the matter extremely pragmatically. They calculated how much it would cost to develop an absolutely new machine from scratch, with a new fuselage, a new power plant, new tests. The figure turned out to be higher than the cost of refining the already existing tiltrotor. The conclusion was simple: it is cheaper to cure than to bury. But it is one thing to make a decision to continue. It is quite another to understand exactly what needs to be changed in the design so as not to face the same problem again. Specialists from the National Aeronautics and Space Administration were brought into the work, an organization that by then had been studying the behavior of airflows in a wide variety of conditions, from the Earth's atmosphere to space, for decades. It was their experience in aerodynamics that allowed them to look at the problem of the vortex ring state not only from the point of view of test pilots, but also from the point of view of pure flow physics. A room full of engineers, graphs laid out on the table, and telemetry records from recent flights. Someone points on the screen to a slow-motion recording of the machine's descent, dissecting frame by frame the moment when the lift begins to drop. "Look, right here, 2 seconds before the loss of control," says one of the specialists, pointing to the graph. "So the pilot has these 2 seconds to react," replies another, "or the machine must have the ability to react instead of him." It was this thought, to shift part of the responsibility from the pilot to the machine itself, that formed the basis of most of the subsequent changes. The work took not months, but years. In total, more than 100 individual changes were made to the design, more than 100 refinements. Imagine a car in which, after a series of accidents, engineers revised not only the brakes, but also the suspension, electronics, body shape, and the behavior of the driver assistance system. The work on the tiltrotor was going on roughly on such a scale. The main part of the changes affected the nacelles, those very rotating nodes at the ends of the wing where the engines and rotors are located. It was here, according to the conclusions of specialists, that the key to the problem was hidden: how to make 2 independent sources of lift behave predictably even in the most difficult conditions of descent. The changes affected not only mechanics. A huge volume of work fell on the software that controls the behavior of the machine in the air. After all, if the pilot physically does not have time to react to a sharp loss of thrust in fractions of a second, then this work must be taken over by electronics, warning the pilot in advance or automatically correcting the flight mode before the situation becomes critical. Here, it is worth pausing at one important point. Many complex machines are refined for years after the start of operation, eliminating minor shortcomings on the fly. But in the case of this tiltrotor, the engineers deliberately chose a slower and more cautious path. Before returning the machine to flights with people on board, each change had to be tested, retested, and tested again. Operational testing stretched practically until 2005. This means that about 5 years passed from the accidents of 2000, which forced all flights to stop, to the moment when the military command was finally ready to trust this machine again. 5 years is not an abstract figure in a report. These are thousands of hours of test flights, hundreds of reports, dozens of versions of software, each of which was checked anew. These were years during which the future of the entire program remained in question, and the built machines, for the most part, stood on the ground, waiting for the engineers to say, "Now you can." And so, in 2005, what had been awaited for almost a quarter of a century since the start of the JVX program finally happened. The Department of Defense of the United States of America officially recognized the tiltrotor as safe for full operation. This was not a loud public statement with fanfares. It was rather a dry formulation in an official document. But behind this formulation stood years of work of hundreds of people who refused to admit defeat after the most serious test of strength in the entire history of the program. The machine, which was nearly buried along with its reputation, got a second chance. And now the way was open for her to do what everything was originally started for: mass production and real service. Official recognition of safety is one thing. Mass production and real military contracts are quite another. Between these 2 points, a chasm often lies, which many promising developments never cross. But in the case of this tiltrotor, the chasm was crossed quite quickly. Already in 2008, just 3 years after the official recognition of the machine as safe, A contract was signed for the delivery of 167 aircraft. The amount of the contract was $10.4 billion. To feel the scale of this figure, imagine, with this money, you could build several dozen large hospitals with full equipment, or finance the work of a small city for several years. And this was the cost of only one contract, only a part of the total investment in the program in its entire history. By 2014, that is, about 6 years after the signing of that very contract, the 201st tiltrotor had already been released. This was no longer a handful of experimental machines for testing, but a full-fledged fleet, most of which entered service with the Marine Corps of the United States of America. It is worth recalling who exactly was the main supporter of this machine throughout its difficult history. It was the Marine Corps that for decades, despite all the accidents, delays, and debates in Congress, continued to insist on the importance of this program. And now, almost 30 years after the start of development, their persistence received material confirmation, hundreds of real machines ready for service. But interest in this technology was not limited to the American Armed Forces. Official representatives of the American Military Department repeatedly declared their readiness to supply tiltrotors to Allied states. The list of potential buyers included several countries from different continents at once. Canada, as the closest ally of the United States of America in North America, South Korea and Japan as key partners in the Asia-Pacific region, Israel and the United Arab Emirates as strategic partners in the Middle East. The very appearance of such a list speaks volumes. States rarely show interest in expensive and complex equipment if they do not see real practical value in it. And yet we are talking about a machine that was recently called too problematic and was nearly closed after a series of accidents. An interesting picture is obtained. On the one hand, officially confirmed safety, billion-dollar contracts, a growing fleet, and the interest of foreign partners, a true business success of a program that could have ended quite differently. But does official recognition of safety mean that accidents stopped once and for all? In the real world, where machines are operated in difficult conditions, desert heat, humidity of coastal zones, intensity of combat training, absolute guarantees do not exist. And indeed, accidents involving this machine continued to occur after 2005 and after the signing of major contracts. We will analyze this side of the story in detail later, when we summarize what the program cost and what it ultimately gave in return. In the meantime, the tiltrotor continued to gain momentum in a completely different sense. A growing fleet meant that the machine began to be adapted for a wide variety of tasks, from troop transport to search and rescue operations. The same basic airframe began to turn into a whole family of specialized versions. Car manufacturers have long learned to build different models on the same technical platform, changing the body, interior, equipment, but leaving the general base unchanged. This is exactly how, only in a much more complex and expensive version, they did with this tiltrotor. All versions of the machine are built on the same basic airframe. The differences between them concern mainly the volume of fuel tanks, the composition of onboard electronic equipment, and the set of tasks to be solved. But behind this formulation lies an amazing variety of roles that essentially the same design is capable of performing. Let's start with a version developed specifically for the Special Operations Forces of the United States of America. It received the designation CV-22B. Its key feature is an increased flight range due to additional fuel tanks, as well as special equipment necessary to perform tasks in conditions of increased secrecy and at a great distance from supply bases. If the CV-22B was created for a narrow circle of specialized tasks, then the next version became the true workhorse of the entire program. We are talking about the modification MV-22B, developed for the Marine Corps of the United States of America. It was the Marine Corps, as we said earlier, that was the main driver of the entire program for decades, and the MV-22B version became the direct embodiment of their requirements. This machine is capable of taking up to 32 paratroopers on board in one flight. This is roughly the capacity of a small tour bus, only delivered by air directly to its destination, bypassing roads, checkpoints, and natural obstacles. An important detail, this modification is capable of taking off and landing on the deck of a ship. For amphibious operations from the sea, such a capability is critically important. The machine turns into a connecting link between the ship in open water and the landing point on land, without the need for intermediate airfields. The next version solves a completely different task, not combat, but logistical. The modification CMV-22B was created specifically to provide cargo and passenger transport. Its difference from the basic version is additional fuel tanks, which allow to increase the range of action during transport missions, where not so much the speed of landing troops is important, but the ability to deliver cargo or people over a significant distance. Further, truly highly specialized versions begin, which mostly specialists and aviation enthusiasts know about. The modification EV-22 was developed to solve radar detection and guidance tasks. This version was created by order of the Royal Navy of Great Britain and is designed to search and detect various objects in the air and on the water, with subsequent transmission of coordinates to other units. Another specialized version is the HV-22, a search and rescue version of the tiltrotor. It was created by order of the Navy of the United States of America and is designed for one of the most noble tasks in aviation: searching and rescuing people who find themselves in a difficult situation, whether on land or on water. Here, those qualities that distinguish a tiltrotor from conventional airplanes and helicopters turn out to be particularly valuable. The ability to quickly fly to a remote area and at the same time land practically in any suitable place. And finally, the SV-22 version, a modification designed for actions against submarines. This direction requires a completely different set of onboard equipment: underwater detection systems, communication means with surface ships, and other specialized equipment housed inside the same basic fuselage. What unites all these versions, despite such a dispersion of tasks, from transferring troops to searching for missing people and detecting targets underwater? The same airframe, the same power plant, the same principle of flight. How is one design capable of solving such different tasks with equal efficiency? The answer lies not in the appearance of the machine, but in what is inside it, and the power plant and systems that make the very phenomenon of turning an airplane into a helicopter and back possible. It is there that we will now look. At the heart of the entire tiltrotor concept are two engines, and the way they are designed and work largely explains why this machine is so complex and so expensive to develop. At the ends of the wing, two Rolls-Royce AE1107C gas turbine engines are installed. They are located not in a fixed position, as on a regular airplane, but inside rotatable nacelles, special compartments that can turn 90 degrees, changing the direction of thrust from vertical to horizontal and back. This capability is the key to the entire concept of the machine. During vertical takeoff, the nacelles are directed upwards, and both rotors work like those of a helicopter, creating lift directly. After gaining speed, the nacelles gradually rotate forward, and gradually the control of lift transitions from the rotors to the wing, just as happens in a regular airplane. This entire transition from vertical to horizontal mode takes only about 12 seconds. Just 12 seconds, less than it takes to read this paragraph aloud, and the machine changes the very physics of its flight. But it is impossible to transition to horizontal mode immediately after lifting off the ground. Until the speed of the machine reaches 180,200 kilometers per hour, the rotors continue to provide the main part of the lift, and control of the machine occurs by changing the pitch of the rotors and adjusting engine thrust. And only after the aerodynamic surfaces of the wing are capable of holding the machine in the air themselves, the nacelles are finally transferred to the horizontal position. Now about the design of these engines. Each of them is built on a modular principle. This means that individual units and blocks can be replaced and serviced separately without disassembling the entire engine. This approach significantly simplifies repair and maintenance in field conditions, far from major technical bases. Each engine is controlled by a digital system, which is called the Full Authority Digital Engine Control System, or FADEC for short. Essentially, this is the electronic brain of the engine, which in real time monitors dozens of parameters: temperature, pressure, speed, and automatically adjusts the engine's operation to changing flight conditions. It was this system that significantly increased the overall reliability of the power plant compared to older mechanical control systems. This power plant also has a less obvious feature, related not to reliability, but to the machine's invisibility to detection means. Engineers provided a special cooling system for exhaust gases, and the hottest parts of the engines are additionally shielded. All this reduces the infrared signature of the aircraft. That is, the machine is harder to detect with devices reacting to heat radiation. Inside each nacelle are located not one, but two separate gearboxes. The first transmits power from the engine directly to the rotor. The second drives the interconnect shaft, a special transmission shaft that runs through the entire wing of the machine from one engine to the other. And here we approach perhaps one of the most important engineering solutions in the entire design. The tiltrotor's engines are mechanically connected to each other through the wing. What does this give in practice? If one of the two engines suddenly fails in flight, the second engine, through the synchronization system, is capable of transmitting power to both rotors simultaneously. The machine does not lose control instantly and does not roll over to one side. Instead, the crew gets the opportunity to make a controlled descent and landing even with a partial loss of power. This decision repeatedly proved to be not just a theoretical backup, but a completely real factor that saved crews in situations where one of the engines failed during flight. The rotors of the machine are also a separate engineering story. Each of them consists of three trapezoidal blades made of modern composite materials. In the hinges of the blade attachment, elastomeric bearings are used, special elastic elements that dampen vibration and reduce mechanical wear compared to traditional metal hinges. The rotation of the nacelles itself, that very process of turning a helicopter into an airplane and back, is carried out using a hydraulic drive. A powerful hydraulic system smoothly and precisely rotates multi-ton units with engines and rotors, and does this throughout just a few seconds of flight. The result is a complex, interconnected system in which mechanics, electronics, and hydraulics work in unison, providing that very effect with which we began our story, when the machine on the move changes the very physics of its movement in the air. But the power plant is only part of the overall picture. An equally important role is played by what the body of the machine itself is made of, and what systems protect the crew in the event of accidents. When engineers design a machine that by definition will fly in difficult conditions and perform risky tasks, it is not enough just to make it take off and land. It is necessary to think in advance what will happen if something goes wrong. And in the case of this tiltrotor, exceptional attention was paid to such thinking. Let's start with the very body of the machine. The fuselage is made according to a semi-monocoque scheme. This means that the load is carried not only by the internal frame, but also by the outer skin itself, which makes the design both strong and relatively light. In cross-section, the fuselage is rectangular, which simplifies the placement of cargo and troops inside. On the sides of the fuselage are located special fairings, or as engineers call them, sponsons. These are not just decorative elements of the skin. Inside them, the main landing gear retracts. Additional fuel tanks and part of the onboard equipment are also located there. In the front part of the machine is the cockpit, and here begins a truly serious conversation about protecting the crew. The pilot seats are ejection seats and fully armored. Each of them is capable of protecting a person from being hit by 12.7mm caliber ammunition. The crew of such a machine usually consists of 3 or 4 people, and for each of them, the armor of the seat is not a formality, but real protection in the most stressful situations. The main volume of the fuselage is occupied by the cargo passenger cabin. It is there that paratroopers, equipment, or cargo are placed, depending on the specific mission. For loading and unloading, a 2-section door is provided on the right side of the machine, equipped with a ramp. Now let's go up to the wing. It is built according to a box girder scheme with 2 spars. This is a design in which the power elements form a kind of closed box inside the wing, giving it exceptional strength with a relatively small weight. The wing has a small angle of forward sweep and is almost entirely made of modern composite materials. The wing is controlled by 4 moving surfaces, which are called elevons. They simultaneously perform the functions of ailerons and elevators, combining 2 control tasks at once. How is a pilot capable of managing such a complex machine in which 2 independent engines constantly change their position in flight? The answer is through a fly-by-wire control system, supplemented by hydraulic actuators. Essentially, the pilot's movements are converted into electrical signals, which then control dozens of hydraulic and mechanical units throughout the machine. The tail unit of the tiltrotor is twin fin, and it is also almost entirely made of composite materials. The total area of these fins is 12.45 square meters, a size comparable to the area of a small city studio apartment. The landing gear of the machine is 3-point and retractable. The nose gear folds back into a special compartment of the fuselage. The main gear during flight hides in those very side sponsons we talked about a bit earlier. Special attention should be paid to the fuel system. The tanks are placed in several places at once, in the wing consoles and in the fuselage sponsons. If necessary, additional containers can be installed in the cargo cabin. An interesting detail: in the version developed for Special Operations Forces, the total capacity of the tanks is noticeably larger than in the variant created for the Marine Corps. After all, such missions often require a much greater flight range. All fuel tanks on this machine are self-sealing. This means that they are capable of withstanding the hit of 12.7 mm caliber ammunition without a critical fuel leak, as well as maintaining integrity when falling from a height of 20 meters. Additionally, a system for pressurizing the tanks with inert gas is provided, which reduces the risk of ignition of fuel vapors. The fuel supply itself is arranged in a strict automated sequence. The engines consume fuel from small feed tanks, which, in turn, are constantly replenished from the main containers. Moreover, even refueling is possible right in flight. The corresponding node is located in the nose of the fuselage. As for the electronic equipment, the onboard equipment includes an inertial navigation system, a radio compass, an altimeter, and a landing radio system. In the cockpit, 4 multifunction displays are installed, as well as a separate screen that displays general information, maps, video from external cameras, various auxiliary images. But perhaps the most important thing in this entire design is not individual technical decisions themselves, but the general philosophy that guided the engineers. All key systems of the machine are intentionally separated from each other and duplicated where possible, so that the failure of one node does not turn into the failure of the entire machine at once. Gearboxes and engines are specially placed as far as possible from pilots and paratroopers. The rotor blades are made of high-strength composite materials capable of withstanding serious loads without destruction. The landing gear is structurally designed to fully absorb the impact energy when landing at a speed of up to 30 kilometers per hour. That is, even a sufficiently hard landing should not lead to the destruction of the machine. The design of the cockpit is additionally reinforced to protect the crew in emergency situations. And finally, a detail that rarely catches the eye, but can be decisive in a critical situation. In the event of a forced ditching, the fuselage of the machine retains buoyancy for 10 minutes. This is not a random figure. This is exactly how much, according to engineers' calculations, the crew and passengers need to leave the machine and reach rescue means. The result is a machine in which literally all scenarios are thought out, from the failure of one engine in the air to a forced landing on water. But here arises the main question of our entire story. Was all this thoughtfulness worth the price that had to be paid for it in money, time, and reputation? We promised to return to the topic we raised back in the section about the contract for billions, to the question of whether accidents involving this machine continued after it was officially recognized as safe. The time has come to fulfill this promise and summarize. Let's start with the most painful moment in the history of the reputation of this machine. In 2007, the influential American publication Time put a photo of the tiltrotor on the cover with a caption that called the machine a flying shame. For a program in which decades of work and huge money had already been invested, this was a true reputational blow, and a public one, in full view of millions of readers. And it was not only about a loud headline. According to most experts, the total cost of the entire program for the creation and production of this machine exceeded the mark of $50 billion. This is an amount comparable to the annual budget of a small state, spent on the development, testing, and production of a single type of aircraft. There were enough complaints regarding the daily reliability of the machine. During the operation of tiltrotors in Afghanistan, the resource of their engines was only about 200 hours of operation, several times less than that of the CH-46 Sea Knight helicopter, which was used for similar tasks. A car engine that needs to be overhauled several times more often than that of a neighboring model performing the same work. This is roughly how this difference looked in real operation. In the first years of service, ground technical teams also had purely practical difficulties with maintaining these machines. The tiltrotor turned out to be much more complex to care for than the usual helicopters and airplanes that mechanics were used to over the long years. There were also new accidents after the machine was officially recognized as safe. In the period from 2010 to 2015, 7 serious incidents occurred, as a result of which 8 people were killed and several dozen more were injured. Moreover, these accidents occurred both on the territory of the United States of America and outside its borders. It would seem that with such a list of complaints, from sky-high costs to continuing accidents, it would be logical to finally write off this machine as a failed project. But reality turned out to be much more complex and ambiguous. The fact is that the speed and carrying capacity of the tiltrotor in many ways offset its main shortcomings. Yes, the machine turned out to be expensive. Yes, it is complex to maintain. But it gives the troops what no other production aircraft in the world can give: the ability to take off vertically from practically any point, and at the same time fly over distances and at a speed inaccessible to conventional helicopters. This is why the military command, despite all the difficulties and reputational blows, did not abandon this machine. After the official acceptance of the tiltrotor into service, most of the original problems were eliminated, or at least significantly mitigated. And here lies, perhaps, the main paradox of this entire story. A machine that an authoritative publication once publicly called a flying shame, according to a number of specialists, today demonstrates a fairly low accident rate. Moreover, some authors generally call this tiltrotor one of the safest aircraft in its class. The same machine, both a shame on the cover of a magazine and one of the safest aircraft according to statistics. How can two such different assessments relate to the same object? The answer is simple. A reputation is formed quickly, usually around the loudest and most tragic episodes. And objective statistics accumulate slowly, over years, and rarely get on covers. The story of this machine does not end there. In recent years, it became known about the development of a new tiltrotor, which received the name Bell V-22 Valor. Over this project, Bell Helicopter and Lockheed Martin are jointly working. The machine was officially presented in 2013, and the first flight of the new aircraft was planned for 2017. It turns out that even after decades of disputes and disagreements, the very concept of a machine capable of combining the vertical takeoff of a helicopter with the speed of an airplane did not just survive, it continues to develop and receive new successors. Recall how we began this story. The desert near Tehran, April 1980. A plan that looked logical on paper, but broke against harsh reality. The Army simply did not have the right equipment to perform the task. Then, among the wreckage of that failed operation, an idea was born that at that time seemed almost fantastic. A machine that would combine the best of a helicopter and the best of an airplane. A machine that did not exist anywhere in the world. The path from this idea to a real aircraft took almost 30 years. During this time, several generations of engineers changed, more than $50 billion were spent, more than 100 individual design elements were tested and refined. The program was tried to be closed several times. It was publicly called a flying shame. It was questioned in Congress, in the press, among the military themselves. And yet, this machine did not just survive. It became the only production tiltrotor in the world, a technology that exists not in a single copy for air shows, but carries real service for several decades in a row. Was all this worth such huge money, such long years of development, and such a number of difficulties on this path? There is perhaps no single answer to this question. It is too easy to look differently at the final balance between costs and results. On the one hand, before us is one of the most expensive and one of the most controversial projects in the history of military aviation. A program that stretched over decades, survived many accidents and reputational blows, each of which individually could put an end to a less stubborn project. On the other hand, before us is a unique technology that really works as originally intended. A machine capable of taking off vertically from practically any point and at the same time overcoming great distances at the speed of a full-fledged airplane. A capability that is still not possessed by any other production aircraft in the world. There is also another lesson in this story, much more general than the fate of one specific machine. A lesson about how difficult it can be to bring a truly new technology to the end. A technology that does not improve an existing solution, but creates a completely new category that has no analogs, and accordingly, has no ready answers to emerging questions. When engineers faced the effect of the vortex ring state in relation to two independent sources of lift, they simply had no one to ask for advice. Such a problem did not exist before because such machines did not exist. The answer had to be sought from scratch, step by step, at the cost of years of testing and difficult losses. This is, perhaps, the main feature of any truly breakthrough technology. It does not appear immediately in an ideal form. It goes through a series of mistakes, refinements, and difficult decisions before it becomes what it was meant to be from the very beginning. And today, years after the first flight, this story gets a continuation. A new tiltrotor, the Bell V-22 Valor, is already being developed, taking into account all the accumulated experience, all the lessons learned, at a dear price over the previous decades. This means that the path traveled by the first machine was not in vain. It became the foundation for the next step in the development of this direction of aviation. You can draw a parallel with how many other breakthrough technologies in human history developed. The first cars broke down more often than they drove. The first aircraft of the Wright brothers stayed in the air for mere seconds. But it was on the basis of these imperfect first steps that everything we today consider familiar and reliable was built. Perhaps in 20 or 30 years, when tiltrotors become a more common and familiar type of aircraft, this machine will be remembered as a pioneer. Imperfect, expensive, causing a lot of controversy, but paving the way for everyone who comes after. The story of this machine is, first of all, a story of perseverance. A story of how an idea born from the failure of one specific operation, contrary to all difficulties, financial and technical, turned into a really working technology that changed the understanding of what is possible in the air. And, probably, that is why this machine continues to cause so much controversy even decades after its creation. Because it was never a simple story of unequivocal success. It was, and remains, a story of a complex, expensive, but ultimately accomplished breakthrough.